Speaker on the program comes from the Research Coordination Network that I mentioned to you earlier from the National Science Foundation. This is Dr. David Vaccari from the Stevens Institute of Technology. He's going to give us a summary of some synthetic global scale work that they've been doing on the phosphorus flow system.
All right, thank you, Jim. So, Jim, you say this is a room full of nerds. I'm about to put that proposition to the test. Do I have a handy device here?
Pointer.
And pointer, thank you. Okay. All right, so some of you may be familiar with the different material flow analyses that have been published for global flows of phosphorus and regional flows of phosphorus. What we've done here is take that and turn it into more of a mathematical model so that you can test some questions and probe it and answer some questions about what that tells you about the system. So my collaborators include Steve Powers right over here, and Tom Buolsema at that table, and Xin Liu, who's way over there in Nanjing, China right now. So a little bit of motivation here is just looking at some the trends for phosphorus production. This is global phosphorus production for the USGS, and we can see that looks like it's going through the roof there. Coupled with population trend, we have it's popular to say that population is going up exponentially, but it's not. It's going up pretty much linearly globally, but that rate has been pretty consistent for a number of decades. But if we take the ratio there and look at the per capita production at the mine of phosphate rock, for most of which goes to fertilizer or other agricultural uses, even that has been increasing significantly. And a lot of that increases from China's increasing their production rates. And this would seem to point to we have a problem with long-term sustainability. How long can we keep doing this? Because this is on top of the population growth. And the good side of this is that the percentage of hungry people in the world has declined over the past few decades, although the number has not changed. But so our population is going up. All those new people we're making are not fitting that category of hunger. So here, this is the trend for the United States, and it tells you something about the sustainability problem that we have. We're in a decline as we're using up our easily exploitable resources, and as a result, our net export, and we were an exporter, has now gone negative, so we're a net importer of phosphate rock. The U.S., you may know, has over the past century, produced about 25% of the world's phosphorus resources. But today, we produce about 11%, and we're still in the top three. China is over half, and Morocco, Western Sahara is similar to our level at 10%. But when you look at the reserve picture, the estimates of exploitable resources, that's dominated by Morocco and Western Sahara, and I'm sure everyone knows about that, with about 71% of the global reserves. If we take that ratio and come up with that lifetime, okay, we know all the caveats about that, the resource consumption lifetime, there are, that both the numerator and denominator are subject to change. Nevertheless, this gives us a number in years that we can view as a planning horizon, if nothing else. And I would say that the Morocco number doesn't really mean anything, but okay. Because it's currently only producing 10%, but what's going to happen when China and the US, on the same time scale, in a matter of decades, starts to approach that planning horizon? We don't like to say run out anymore, but maybe run low might be a reasonable way to describe what's going to happen. Globally, we have several centuries, but we still have a shorter term problem in terms of resources. So that's the motivation here. That's a graphic of the reserve situation showing the dominance of Morocco and Western Sahara. So this study, we are examining the flows of phosphorus mostly through the agricultural system, and we're looking at possible strategies to extend our use, to more efficiently use our phosphorus resources. And we look primarily at these 6 interventions that different individuals have proposed, which is encouraging limitation or even reduction in the amount of meat and products in the diet, certainly improving agricultural phosphorus use efficiency, reusing manure to a greater extent, and we just heard about food waste improvements, and that's become much more of a public issue. Aligned with food waste reduction is recycling food waste and also recycling human waste. So these are all things that we can imagine that are interventions in the flow of phosphorus through our food system. So this is what we call substance flow analysis, and you've seen different forms of this, I'm sure. Starting with, we've got to change the batteries in here, Jim.
Not my thing.
Phosphate rock on the upper left there. Those dark green lines coming out of the top, you see phosphate rock towards the middle. NS is natural sources to croplands, and on the right, G is natural input of phosphorus to grazing lands. Those are the 3 inputs to the system in this model. Now, we could always envision more complexity to the model, but this is a starting point based on some of the published substance flow analysis. So the picture here is a conceptual model. So phosphate rock is produced into phosphoric acid, makes fertilizer, applied to soil, taken up by crops, harvested. Some goes to animals. You get a recycle loop there with the manure. Try again with this light. No. Oh, you know what it was? My thumb was in the way, Jim. We have a significant recycle loop here of returning phosphorus to the soil and producing food consumed by humans. And then we have these various leaks from the system, losses of phosphorus. The 6 interventions that we're considering are increasing human waste recycling, increasing the recycling of food waste, reducing the amount of food waste, reducing amount of animal food in the diet, increasing manure use. I think that number is wrong. I believe it should be more like 50% is the nominal manure use efficiency. And phosphorus use efficiency, reducing some of these leaks from the system, erosion loss, soil storage, crop loss, and so on. So the question is then, if we change these parameters, how much of an improvement do we get? And where do we get the best bang for the buck? So this shows another example of a substance flow analysis just for the US. It's very similar. One thing that you don't see in the global one that is in the regional scale or national scale one are imports and exports, but otherwise most of these flows have analogs at the global level. So the model is demand driven. It starts with our dietary need for phosphorus and then kind of works backwards from there to determine how much phosphorus we're going to have to mine to satisfy that need on top of these natural sources and so on. There are a number of parameters. The 6 parameters that I've already defined are these efficiency parameters, these interventions. Several of these inputs, including human population and the per capita dietary phosphorus demand. And then there are a number of other parameters that we're not going to consider as interventions. They could be, but we didn't include them in this study, such as the percentage of our human waste that goes to the landfill, the percentage of crop uptake that is lost by erosion, which is one of the major losses or leaks to the system, and so on. So to give you a feel for how we propagate from human consumption on back to the phosphorus that we're going to require from production at the mine, I'll just go show you the first couple of steps here. And this is just mathematically kind of simple. It's just implemented in a spreadsheet and simple relationships. So if we start with the phosphorus in the diet, human waste is just going to be the same as the human consumption, so that's a 1-to-1. And then to calculate the wastewater that gets recycled, we just multiply that by, well, here's one of our efficiency parameters, the waste recycling efficiency, times the production of human waste gives us the amount that goes back to the soil in that flow. Similarly, we use these proportionalities to calculate how much goes to landfill and surface water. Then here's another of our interventions, the food waste fraction. If we divide by the fraction not wasted, we get the amount of food supply that we have to produce in order to get that human consumption. And then a fraction of that is animal food, and then the difference is our vegetable food, and so on. And then we work our way backwards through the whole flow. The whole picture, so what I just showed you is this part here, and then we just continue from there, calculate the food waste, calculate how much animal production and manure is involved, and then your crop harvesting. You do a balance around the soil. We can see some of these other parameters coming in. Here's where phosphorus use efficiency comes in when we're calculating the amount of fertilizer we need. Then we get fertilizer manufacturing, and then you finally come up with the bottom line. There it is. Amount of beneficiated phosphate rock that ultimately comes from those assumptions and this phosphorus in the diet. So let me move on to results. I think that's what's of most interest. What we're looking at is the sensitivity of the system to those 6 interventions. That is, if we change that intervention, we change human waste recycling by 1%, how many percent do we have to change? Do we change phosphorus production at the mine, the demand for phosphorus production at the mine? And what you see, these are the 3 least sensitive. The blue line, the dot shows the current condition, and this is for food recycling efficiency. And you can see it's kind of flat. That means it's not very sensitive. Changing food recycling efficiency just doesn't change how much phosphorus you draw from the mine by a heck of a lot. The human waste recycling efficiency, a little bit more sensitive. And if we drive it to 100%, you can see how much we've kind of reduced. Well, human waste is about 17% of the phosphorus we're mining. So the best we can do if we do 100% recycling would be reduce our mining by 17% or so. And then this one is manure use. If we increase from using half of our manure to 100%, well, there we do get a substantial improvement in reduction of phosphorus from the mine, up to close to half the amount of phosphorus. Now here's the advantage of the model. This was a surprising result. A model is a way of codifying what you know. And when we learn something, we're kind of making a model in our brain, right? So a mathematical model is something like that. It's a way of codifying these relationships, and then we can probe that model and ask it these kinds of questions and say what it tells us. So this was one that's a surprise. The effect of animal food in the diet, and we're here nominally. If we drive it down, we see, not surprisingly, that we're using less phosphorus. But we reach a discontinuity where it suddenly starts going the other way. Well, how can that be? Well, the reason is because of this natural source of phosphorus to pasture lands, providing some of the phosphorus in our animal food. If we decrease the amount of animal food in the diet, we reach a point where it shuts off the fertilized contribution. These are both fertilized contributions to animal feed. Those you don't need them anymore if you aren't producing that much animal food. And now you're relying only on this external source. If you reduce further than that, you're using less of this and relying more on vegetable food, which actually increases the amount of phosphorus that you have to get from the mine, assuming you don't change anything else, any other parameters. So that's surprising and interesting result. And I mean, we can refine the model, and I think we would find that it might not be such a sharp break, and there might be additional details that would come out, but this is what we find from the current assumptions and what we know right now. The other interesting thing shown here is the interaction with manure use efficiency, because one of our hypotheses was that if we recycle more manure, well, that might reduce the sensitivity to animal food in the diet. And that's true, but maybe not quite as strong as we expected. So these the blue and the green lines are at different levels of manure recycling. Even if you recycle the green line 100% of your manure, you don't wipe out this effect of reducing animal food in the diet. So that's an important thing. And this is the reason, as most of you probably know, moving up, kind of up the food chain here to beef uses more resources in terms of grain and so forth. We could also achieve a similar effect if we, rather than reducing the meat in the diet, we could just move to one of these less resource-intensive forms of animal protein. And the other interventions are phosphorus use efficiency. This blue dot actually should be around here. The slope of this line is that sensitivity I'm interested in, and this is the food waste fraction. These are two of the most sensitive among those 6 parameters. So this is turns out to be really important. And then the other thing that you see here is there's kind of a limiting effect as you drive towards a theoretical perfection. The curve flattens out as you decrease your food waste. It still improves, but less and less as you go along, and similarly for phosphorus use efficiency. So to summarize all of these, just at those, the current nominal conditions, those where the dots are on those graphs, the slopes of those curves are the sensitivity. This says that food waste recycling efficiency, if we improve that by 1%, we would decrease the demand for phosphate rock by 0.012%. It's a very low sensitivity. Doesn't mean we shouldn't be doing that and that it's not important, but relative to the other things, that's our lowest nominal sensitivity. Now, one thing that we did not consider here is the cost of these different interventions. So, for example, manure use efficiency, also kind of low. You get less than 0.5% improvement for each 1% improvement in manure use. But we didn't. But that would probably be less costly, I think, than, for example, to get people to eat less meat in their diet. That's a more difficult thing sociologically to achieve. The other fascinating thing I think about this is that again, now you see the animal use in the diet, animal fraction in the diet, and phosphorus use efficiency are relatively strong. You get much more than 1% improvement for each percent change in your parameter. Particularly, I like this one. Looking at the food waste fraction, it's about 1, compared to food waste recycling. Reducing food waste is about, under nominal conditions, about 80 times as effective as increasing your recycling of food waste. I think that was a sobering value to me. We've often heard that reduction is better than recycling. This puts a number on it. And that's a useful thing to know. Now we have to multiply them by the costs of doing those things and see what that ratio comes to. So this also looks at the effect of population. I'll kind of pass over this. You get these breakpoints also because of those constraints in transferring to external, to the natural flows. The effect of population at different meat and diet levels. Or animal food diets. I changed the acronym here, I apologize. In other places I put AFD, animal food in the diet, and I had originally put meat in the diets. I've got to change the acronyms in some of my figures here. But the purpose of this figure was to kind of drive this towards 0 to come up with this idea of the minimum population that could be supported if we had no if we were only using renewable sources of phosphorus, which excludes mining of phosphorus. So, and this is without we would assume that if for some reason we had to do this, we would, or farther in the future, we may have to have much more intensive recycling to achieve renewable, reliance on renewable phosphorus exclusively. Other part of the demand besides population is that actually we anticipate that meat requirements are going up also pretty steadily. Each form of meat. And with regard to population specifically, remember I said that population has been increasing linearly, increased about 80 million people per year. That's how much we add to this earth every year for the past few decades with some ups and downs. This is from the United Nations Environment Program population projections from about 2 years ago, and I understand they have a new one out. I have to revise this slide, and they've corrected this. So I took their projections and I calculated the differences, and saw that their future projections say that oh, we've been going along like this. Well, now we're going to start decreasing every year until we're going to hit zero towards the end of the century, which I thought was tremendously optimistic. I understand the new projections are not quite as rosy. And Steve, you said that this had us leveling out at about 9 billion. And I think what's the new projection by the end of the year is about 10 billion or 10 plus, something like that. Well, what? Okay, time, okay. I am close to the end. These are the conclusions. I'll just focus on this one, that the sensitivity that I have just presented have to be interpreted in terms of cost of implementation. And then the other ones just relate to these relative amounts of the sensitivity. So, the models can always be improved. George Box said, all models are wrong, some are useful, and I hope that this one has some useful results. What we need to do is maybe go to deaggregate by region. So that's a global model, so it kind of averages things. Like it includes soil storage in as a global average, but some areas store soil, some areas are mining the soil for phosphorus. Turn into dynamic models and so on. So I think that's about it. Thank you. And any questions are welcome.
Dave left some time for questions, so please fire away.
This is the test of the nerd part. Yes?
Yeah, thanks. Very interesting talk. With any model, there's a calibration needed, and I'm wondering how you've thought about how this is calibrated to real-world data. Obviously, you've integrated some real-world data, but are you able to test it in other ways?
Yeah, we're struggling with that, and I think we can justify all the numbers. Among ourselves, we were just having discussions about, for example, the value of NS, the natural source of phosphorus to crop lands. And we might even make a change to that and reevaluate that. But I've looked at the sensitivity of all those parameters, and we're focusing on the ones that are most sensitive. But we've tried to justify each one by different references in the literature, and we're close to finishing a paper about this model that will explain the sources of all those ratios and assumptions. Did you have a bit?
Do you have to follow up, or it's a follow-up?
Okay. So Tom is one of the co-authors of this paper.
Yeah, it's been quite an eye-opener to participate in this process. I come from more an agronomy background, so I had opportunity to look at some of the parameters, especially related to the agriculture component of the model. The one comment in response to your question, which is a very good question, how do you relate it to the real world? And as Dave mentioned, every parameter in there is a peer-reviewed literature reference to it. But I'd have to point out that some of the greatest uncertainties are associated with the greatest flows as well. And defining exactly what area we're related to is a challenge. Another challenge is this is a global model, treating the world as one uniform thing. And it ignores the fact there's huge amounts of spatial variation within countries and among countries as well in terms of phosphorus flows.
And that could be significant because this is a nonlinear model. So the results are not necessarily additive from different regions. So that's It's just a first step. Yes, sir.
Just, excuse me. On your model, you had mentioned loss of phosphorus from the systems.
Yeah.
Were you able to do any predictive work with this model by changing those efficiencies showing up in environmental risk or reductions in environmental risk?
No, but that's another thing that could be done. Once you have this model, it can be linked to like a life cycle analysis for phosphorus, so that they do. I've seen this done in other contexts where they link life cycle analysis with material flow analysis or substance flow analysis. So we could take, just as I said, we can look at the costs, link our costs with these interventions. We could also link the environmental costs of some of these leaks from the system and figure out how those parameters change that cost.
Did we pass as nerds?
Yes, flying colors. Excellent, excellent question. Yes, sir.
Hi. In your model, if you increase manure use as fertilizer, that has a very high impact. But did you include the parameter that if you take all the manure for crop fertilization, you will need to fertilize the grassland? Because the level of phosphate in the grassland is going to drop, because it's naturally fertilized by the manure itself.
A big question is so some of these flows we can distinguish. I would think of that as probably more of kind of a loop within the animal component here, but I think we have to go back to the original source of where we're saying that the half of the manure that's produced is shown here as returning to the soil. According to this model, it's going to cropland. Okay, so we know that some of it simply doesn't leave the pasture lands. I don't know if that's included in here. I think we need to go back to the source of those data to find out that manure production, is that what's included there, and how much of that stays within this component versus that certainly is one of the big contributors to this particular leak, the manure that's lost to the environment. But I think of manure that's lost largely to the concentrated feeding operations that being spatially separated from where the grain is produced. So they make these piles of manure, and there's great amounts of runoff from them in certain regions anyway.
So Dave, you emphasized.
Where are we? Oh,
Hi.
Bruce.
You emphasized this roughly 80-fold advantage of reducing food waste versus recycling, and so I can sort of understand that quantitatively, but 80-fold seems like a lot. So how does the model explain this big difference?
I would describe it this way: if we reduce food waste right here, we shrink this, it shrinks everything. But if I shrink this thing here, which is the food recycling, I'm returning some of my phosphorus here, and then that goes through all these losses. That's why it's less effective. So recycling is subjected to the losses that the regular phosphorus is, but reducing the waste shrinks the whole system.
Okay, we'll take one more, and then we'll be, and then there's another one. Ready for break.
I'm just wondering if you are imagining this becoming something in the public domain or something available as a model, as a spreadsheet, or is it?
What we anticipate doing is when we publish it, the spreadsheet itself will be in the supplementary material. So yes, people can probe the model themselves, modify it to their content, and so forth. Yes.
Okay, so let's thank Dave
Okay.
again.